Alright guys, so let's get into some review problems for rational functions, expressions, and equations. So the first couple here are to identify holes, vertical asymptotes, and horizontal asymptotes. And then we should also be able to sketch the graph. I actually just typed this into Desmos just to get an idea of it, but we'll kind of walk through some of the things that we should be familiar with. But first off, let's take a look. To get the holes in the graph, that's going to be when you get a factor that cancels in the numerator and the denominator. So we'll come back to that in a second. But vertical asymptotes are going to be anything that makes the denominator 0 that does not get canceled out. So let's think about this function here as 1 over x squared plus x minus 2. I know that x squared plus x minus 2 is factorable into x plus 2 times x minus 1. Okay, so this expression could be written as 1 over x plus 2 times x minus 1. So you really want to try and factor anything that you can. It's going to make some things easier. So in this problem, nothing cancels because the numerator is just 1. But we do see that we get two restricted values from the denominator, and they're both going to be vertical asymptotes because, again, nothing got canceled out. So we get a vertical asymptote at x equals negative 2 and also at x equals 1. And you can see those on the graph here, right? Here's the negative 2, where the graph does not go through, and then here's the positive 1 as an x value that the graph will not go through. Again, as far as holes, there are none because we weren't able to cancel any factor in the numerator and denominator. So the only restrictions are both the vertical asymptotes there. Now, as far as horizontal asymptote, that's the one where you want to look at the degree, and it's kind of saying, in the long run, what is this function's value approaching? So it depends on the degree, and in this case, the denominator's degree is higher. The denominator's degree is greater than the numerator's degree. In that case, the horizontal asymptote will always be y equals 0. Okay, and you can see that here in the end. If you remember when we talked about end behavior, the branches of this graph here, as this continues out, are just going to approach 0, and they'll never quite reach 0. But anytime that denominator's degree is larger, that's what's going to happen on the graph on the ends, and that's going to lead to the horizontal asymptote. Okay? All right, then we get into some simplifying expressions and stating exclusions. So let's take a look here. Again, this is where you just want to start factoring and see what happens. So that numerator, I see there's a common factor of 5n, and we'd be left with n plus 3 to get the original numerator back. And there is an n plus 3 in the denominator. Okay, so if we keep simplifying, n plus 3 divided by itself is going to cancel out. So the simplified version is 5n, and our restriction now from the denominator is that n cannot equal a negative 3. Okay, number 4. We have, again, some expressions that we can hopefully factor and reduce. So the m squared minus 5m minus 6. So we need factors of negative 6 that'll add up to negative 5. So we could do m minus 6 times m plus 1. And the denominator, factors of 54 that add up to negative 15 would be m minus 9 and m minus 6. Okay, so I see again that we're going to have a common factor of m minus 6 cancel out to give us a final simplified version of m plus 1 over m minus 9, but with two restrictions. Remember, original denominators, m cannot equal 9, m cannot equal 6. Alrighty, and some more simplifying here. So this is going to be, so we're multiplying expressions. So basically it's similar to what we just did, except we will need to actually multiply the numerators and denominators together. But we're just going to simplify things first, factor, and see what happens. So we have 1 over 3a squared. Nothing I can do there. The other term, let's see, 10a squared plus 60a. It does have a common factor of 10a. So it would be plus, times a plus 6, right? That would get us back to the 10a squared plus 60a. The denominator, a squared plus 9a plus 18. Any factors of 18 that add up to 9? Yeah, 6 and 3, right? A plus 6 times a plus 3. So we got everything factored. I do see at least an a plus 6 that will cancel out. And then what we can do, there's an a, let me highlight. there's a factor of a here, and then there's an a squared down there. So if we wanted to, or we should, the 3a squared is really 3 times a times a. So the a I have up here will cancel one of those a's. Okay, so we're still going to have in the numerator just a factor of 10. The denominator, we have a 3, we have an a, and we have an a plus 3. And now you can leave it like that, if you wanted to distribute the bottom together, you could as well. But this would be totally fine as well. Okay, and this one, directions didn't say anything about stating restrictions, so I'm not going to do it. Okay. Number 6, fraction divided by a fraction. So I'm automatically thinking multiply by a reciprocal. Okay, so let's first factor, though. That first term on the left is going to stay the same. So the p squared plus 6p minus 7 is factorable. And p plus 7 times p minus 1. It's over p minus 1, so those will cancel for us. Now I'm going to multiply by the reciprocal, so we're going to do a 6 on the numerator. Factor a 4 out of the 4p plus 28. Okay, so we have 6 over 4p plus 7. Now we're going to have some common factors divide themselves or cancel themselves out. So the p plus 7s cancel. P minus 1 over p minus 1 cancels. We are left with 6 over 4, which is actually reducible, right? 6 over 4, if you divide those both by 2, would become 3 over 2. Okay, so this thing's just going to equal a whole number, 3 over 2. Jump to, I got number 2 written on a clean page here. So again, I threw the equation into decimals just to get an idea. Let's kind of make sure we're clear with where everything's coming from. So again, I'm going to try to factor everything that I can. So that numerator, the x squared plus 7x plus 12, I can find factors of 12 that add up to 7 using x plus 4 times x plus 3. And then the denominator, it's 3x squared plus 12x. So there's actually a common factor in there of 3x. And then we would be left with x plus 4. Okay, so everything has been factored completely, and now we should notice that there's a common factor of x plus 4 that can be reduced. So this thing in its simplified version would be x plus 3 over 3x. Okay, so if we just had to simplify, that's what it would look like. Okay, this is going to help us get our restricted values, and we are going to notice that the restrictions, okay, which will be a whole or vertical asymptote. Okay, again, I'm looking at that denominator, and I want to list these before I canceled anything. So there was an x there, and there's an x plus 4 there. So when x equals 0, okay, that's the one that would make this factor 0, we're going to have a hole in the graph. I'm sorry, that's going to be the vertical asymptote, because that factor did not get canceled out. That's still there. Okay, but the other factor, the x plus 4 factor, did get canceled out. So that means when x equals negative 4, we're going to have a hole in the graph. Okay, so when you graph this thing, you need to make sure we are clear. There's a vertical asymptote right through here, right through x equals 0, as you can see on the graph. But also at x equals negative 4, there is a hole. So make sure when you draw this, it's not going to show up on decimals. You need to make sure that you put an open circle there to state that there is a hole. Okay, if you made a table of values on these, when x is negative 4, there's not going to be a y value there. Okay, so we need to make sure we're clear on that and that we state that on the graph. Okay, the last thing we need is the horizontal asymptote. Okay, the horizontal asymptote, that's the one where you compare the degrees. So in this case, they are both second degree functions. So when they are equal, that's when we look at their coefficients, and that ratio of 1x squared over 3x squared, the ratio is 1 over 3. That's going to be the horizontal asymptote at 1/3. Okay, as you can see, this thing, it does approach 1/3. It's not approaching 0. I can tell from that. There's a piece up here that goes above 0. And then this piece actually just approaches 1/3 as well. All right, just to kind of add one detail that's not even asked on this question, but we should be able to handle the state the domain and the range here. The domain of this function is, again, asking which x values is it defined for. So it's defined on all real numbers except those two restrictions. So for the domain, we would just list it as x cannot equal 0 or negative 4, because that's where we have the vertical asymptote and the hole. Okay, now for the range, which y values does it go through? So it goes through all real numbers except a few. Okay, it does not go through that that 1/3 where we have the horizontal asymptote. Okay, we can see the graph again kind of just approaches it on the ends here, but doesn't quite get there. And one other piece, there's that hole in the graph. Okay, so there's some y value right at the hole that the graph is going to jump over. And the only way we're going to figure out that y value is plugging in the x value and evaluating it. Okay, so the hole occurs when x equals -4, right? We must plug in -4 into the simplified version, okay? Because if we try plugging in -4 to the original version, we're going to get that 0 in the denominator, and it's not going to be it's not defined. But we can plug -4 into this version. So if we plug in -4 for x, it would be -4 plus 3 over 3 times -4, okay, which is going to be what? -1 over -12, which is actually going to end up being positive 1/12. Okay, so again, all I did there was plug in the x value into each x for the x value of the whole, and that told me what the y value would have been. And you can see right on the graph, it is just a little bit above 0, the y value there. So the 1/12 seems to be accurate. All right, a few more expressions to simplify here. Adding two fractions. So again, the deal here, we're going to need to get a common denominator. So we have one of the denominators is a plus 6 and the other is a minus 5. So I'm just going to have to use them both since they don't have any common factors or anything. We're just going to use the both of them. A plus 6, and we're just going to do some simplifying. So let's figure out the numerator, the left term, has the a plus 6, so we need to multiply top and bottom of it by a minus 5. Okay, now the denominator, notice, would have a plus 6 and a plus 5, right? So the numerator would become, if we multiply that out, 3a squared minus 15a. Okay, that's a subtraction sign in there, sorry about that. Okay, the other term had the a minus 5, it just needs the a plus 6 factor, so we can multiply top and bottom by the a plus 6. Okay, we can go ahead and distribute that out to multiply 4a squared plus 24a. Okay, now that we have everything with the common denominator, we can go ahead and just simplify and kind of add the numerator together. The denominator, again, is just going to be the common a plus 6, a minus 5. If we combine the terms up here, so 3a squared plus 4a squared is 7a squared. And then negative 15a plus 24a will be plus 9a. Okay, and again, you can kind of leave it like that if you want. If you want to factor out, we could factor an a out, I guess, of the numerator. A times 7a plus 9 over a plus 6 times a minus 5. It didn't help because nothing, is going to reduce, but either one of those would be totally acceptable. All right, another one of those, a subtraction problem to simplify. Same concept though, the denominators are just totally different things, so we're going to just use both of them as our common denominator. What we could do for this one, actually, I'm noticing, this one we could factor a 2 out and just get x minus 3. So what we can actually do, okay, if we wanted to, and it might help with reducing later, is the denominator factors are 2, and then that 2 shows up again, and then x minus 3. So we can actually just use the 2 times the x minus 3 as our common denominator, and then we don't have to worry about multiplying the term on the right by anything. Okay, so that's why it does help to factor these. I didn't even notice it right away, but factoring that 2 out makes it clear that all we really need to do to this one is multiply the term on the left, top and bottom, by x minus 3, and just leave the one on the right alone. Okay, so this one's just going to be 3x minus 9. Okay, and the term on the right already had the denominator that we needed. Okay, so it was already set up nicely. So we can go ahead and just write this as a single fraction now, since we have the denominator to be common. And it's just 3x minus 9. If we subtract 5 more, we should end up with 3x minus 14. And that's all we can do there. I can't factor anything else or do anything else. So that is that. Okay, and then finally the equations here. Okay, so let's walk through these. The process I like to use on these is to do what you got to do to get rid of those fractions. Okay, and what that means is it means multiply by the least common multiple of these denominators. So let's do it. Let's factor these first ones out. They can have an x taken out. So x times x plus 3. Same with this one. Okay, and that just helps me see again what it is I'm going to need to multiply by. So I know I need to multiply by x. I need to multiply by x plus 3 as well. Okay, that'll take care of that x plus 3. And then this one's just a repeat of the first one. So if I just actually multiply the whole problem by x and x plus 3, that's going to cancel all of the denominators. Okay, so let's show that step in detail and see what happens. Okay, so then there's a 1 under there. So we're going to multiply, but I'm not going to actually distribute or anything yet. I'm just going to write it out. It's x plus 3 times 1, and the denominator was x times x plus 3. Okay, the middle term here is again x times x plus 3 times the 1 that was right there over x plus 3. Okay, and it's going to equal x times x plus 3 times the 2 over x and x plus 3. Okay, so I just kind of distributed that x and x plus 3. I didn't really multiply yet, but I wrote it out as if it's going to be multiplied. And the reason I didn't want to distribute it yet is because now is the step where we're going to get these denominators out of here. Okay, we have in this first term we have x dividing by x, we have x plus 3 dividing by itself as well. So this first term is really just 1. The middle term, the x plus 3's cancel, so we're just left with x times 1. And on this right term, the x's cancel and the x plus 3, so it just equals 2. Okay, so we have a lot better looking equation, right? 1 plus x equals 2. Let's just subtract 1 from both sides, and we will get x equals 1. Okay, let's make sure that that is not a restricted value. Okay, from the original problem, the only restrictions were if x were 0 or if x were negative 3. So we are good to go with our answer of x equals 1. Okay, so let's finish the last one up same way. This one has denominators of just n squared. So that's what we're going to multiply every term by. We multiply both sides of the equation by n squared. Okay, so the first term is n squared times 1. There's no denominator to worry about. Then n squared times the 1 in the numerator, but it has an n squared in the denominator. And then the far right term is n squared times that whole term, n squared plus 4n minus 5. And it is all over n squared. So let's start doing some simplifying. Okay, first term is just n squared. Middle term, now they cancel out, but be careful. There was a factor of 1 there. So when they cancel out, this equals 1. It doesn't just totally disappear. It was something divided by itself, so it equals 1. And then this term here, the n squareds cancel. We're still left with the n squared plus 4n minus 5. Okay, so it looks like we're going to have ourselves a quadratic. Well, maybe not, because look what happens. We have n squareds on both sides, don't we? When we subtract n squared from both sides, okay, we're just left with 1 equals 4n minus 5. Okay, because those subtract out. Now, if we would have had n squareds left, I would try to get one side to be 0 and then try to factor it and use some quadratic method. Oh, but we're going to go ahead and solve this by adding 5 to both sides. 6 equals 4n. And take the 6, divide by 4. It'll be 6 over 4, which is reducible to 3 over 2. Okay, and again, just make sure that's not an excluded value. In this case, the only restricted value would have been if n were 0 from those denominators. So our answer of 3 over 2 seems to work out just fine. All right, so that's some review problems, rational functions, talked about graphs, finding asymptotes, holes, and then we simplified expressions, and we solved some equations.